Hello, everyone. So imagine you're the field engineer, and then you turn your computer and you find this, right? It goes into an endless reboot loop. You don't know what is going on. So what happens? The error seems not to be a corrupted driver. It doesn't seem to be any ICS known malware, nor an EDR. But instead it's a file system operation vulnerability. So what is that?
So in a file operation vulnerability, a elevated process tries to access some file or a folder that is accessible by everyone, right? So that happens a lot where elevated process needs to access some file. But in that case, they need to handle it correctly. So they need to manage some fail safes and everything. If that's not done properly, then a lot of attack scenarios open up. So you all might be aware with DLL planting or DLL hijack. Attacker can just place a DLL, get shell, whatever. And we will talk about that a bit and look into some other ways we can exploit this privileged file operations and potentially get some privileges. So let's see. So these are the typical example of this users issues. And they are commonly found in installers, uninstallers, and a lot of antivirus where they need to access something less privileged. So in example of antivirus, they need to scan some file, and which could be like of less privileges. And if that's not done correctly, then that could leak credentials or something. So these are kind of operations that are mostly more focused towards this file operation vulnerabilities. So write, move, copy, delete, or even opening a file that can lead to information disclosure. We'll mostly focus on delete operations, which could lead to like file corruption or potentially a denial of service. So this is a typical attack scenario. Let's say in ICS environment, there is an alerts manager, which tries to send an alert, and if something goes wrong, and it could read, it needs some sort of log file, right, to write what happened, something like that. And in configuration, administrator defined a log file path. So when it was initially set up, and at the time of use, it was pointing to a legit log file, right? A time of setup. But at the time of use, attacker can just modify it to a critical kernel driver and replicate what we saw with a lot of EDR agents. So looking into the landscape, we see there are a lot of known CVEs and a lot of vulnerabilities that were found using the same file operation vulnerabilities. And yeah, so how do we find this kind of vulnerabilities? What is the typical research process flow for this, right? First, we need to hunt for it. Look for any potential software that has this vulnerability. So how do we do that? Static testing, something like looking into the binary reverse engineer, how it works, that might not be the best idea for this kind of vulnerabilities, because like, how do we exactly determine? That could take a lot of time and wasted efforts. And yeah, manual code reviews, automated code analysis, it's definitely not worth going through all that hassle for this vulnerability. So what about dynamic testing? Yeah, so I should.
Yeah, so essentially dynamic manual analysis is good if you know which process you're targeting, and that's great if you have an idea, oh, I want to check that software, I know that this might contain a potential vulnerability, that's great. And these are great tools. However, if you don't know exactly which of the software that is running on the engineering workstation is vulnerable to this, you might need to do something more automated. Like that's part of the hunting process, right? So these are tools that will help us later, but for now, let's look at something different. And this with instrumentation might save us. So you might have heard of instrumentation before, and instrumentation is a technique in which you can analyze and modify the functionality of a program without having the source code. You don't need to recompile it, so you don't need any kind of previous information on that sense. You just need the program and know the function that you want to change the functionality of. So it is used for different purposes, mainly testing, some reverse engineering, debugging. It is used a lot for profiling to know how many times a function is accessed. But for our purpose, hacking. So this is what regular function is. This is how a regular function is called. The first image, the caller calls a function, and when it ends executing, it returns to the caller. However, when it is instrumented, you're going to have extra steps, which is you're going to have a detour function, which is your function that you can control the input and output of it, of the parameters that are passed to the target function. And then you have a trampoline function that is used for alignment, and then you just, at the end, call the target function. And then at the end, before getting to the original caller, you also return to your detour function, in which you can modify the parameters of the output of the caller function. And if you Google dynamic instrumentation, most likely you're going to encounter Frida, which is the most popular dynamic instrumentation framework. And it's great. I think you can use it to instrument a lot of different platforms, including Android, iOS, and it's pretty cool. However, I think there's this other platform that is used specifically for Microsoft devices or environments. And I think this is pretty cool, and not much people use it. Or if they use it, I think at least there's not much information, public information about it. And the only group that I've seen that promotes it a lot is Guided Hacking, which is these guys, a group of, they talk mostly about gaming hacking. So they create their cheats based on Detours, some of them. So we wanted to give it some promotion to this tool because it's pretty cool. So the simplest way to use it is through a DLL. Not the best. Maybe you can also implement it through a driver, but the simplest one is through a DLL. And it has so many functionalities, but the main ones are, first of all, the transactions. You can think of it as a database transaction. So you define where the transaction would begin, and before you commit it, you specify what actions are going to be performed. So the next step is you need to know where the function that you want to instrument is. So you need to call this detour update thread to have the pointers, the current addresses of the pointers, and then you call the actual interception, which is detour attach. And it has so many other options, but these are like the ones you need for starting playing with it. And the detour attach, what it does, you provide the library that or the function that you want to intercept, and what is going to be replaced instead of that function, which is our detour function and the target function. Okay, so we know that maybe this will help us to find these kind of issues, but what should we instrument? So since we're dealing with creating files, moving files, deleting files, we needed to check the documentation. And what Windows tells us is that most of the operations, even though when you get to see that there is the lead file and other Windows APIs for many other operations, most of them are, if you look and debug those functions, most of them relied in create file W. And the reason is that depending on the function you call, different flags are passed to this function, and create file handles the creation, override, and moving. Because at the end of the day, if you move a file from one location to another, you are creating another file. So most of the functionality is made through create file and open file. So this is the create file example. And another tip I want to give you is that always look into the most internal function when you are instrumenting. And the reason is you want to avoid two things. First, creating too many detouring functions. And the second thing is that sometimes the programmers remove the symbols. So if you go to the most internal one, most likely they won't be able to remove that symbol. In this case, the most internal symbol is NT_create_file, which is the syscall in charge of creating files. So yeah, most likely the programmer is not going to remove that symbol, right? So, otherwise, they're not going to have a way to create a file. So, and if you see, many functions converge on NT_create_file. So if we just instrument NT_create_file, we're going to avoid creating so many different detour functions for every single operation. That at the end of the day, it's just NT_create_file. And this is a table, a chart that you can check. This is way better than the actual Windows documentation, in my opinion. So you can see all the parameters that are received, how are they passed, and what are those syscalls used for. And it is well maintained as well. It is open source. So the first thing we wanted to do is define. We know that we need to catch empty create file. So we already saw in this table what parameters empty create file expects for. So we define a function pointer as null because at this time we don't know where it is. And then the second step is look for that library. And Detours allows you to, it has a detour find function functionality that it allows you to find where that function is in memory once the program is loaded. So you just need to specify the module, where it is, and then the name of the function that you were trying to instrument. And that's it. So the next step is define a list of users that usually in a system have less privilege to access the files. So this is not an exhaustive list. This is just so it can fit on the slide. But you can put there as many as you want. And basically what these things are, these are SIDs. And SIDs are for Windows a way to define the privilege that each user or group has towards a specific object or file or folder. So in this case, we're defining the most common less privileged users that you can find on every Windows system, like everyone, anonymous, and so on. And then the next step is to put it into a DLL, right? So, and the logic goes as follows. You define the SIDs of the users that have low privilege and that shouldn't access high privilege, either data or programs. Then you create a detour function to catch all the accesses to these operations, in this case, create file. And then we check for the current process integrity level. In this case, if it's medium or less than medium, then we don't care about it, because that's not a potential target that we can abuse, and then we just return. But if that's not the case, we continue our analysis, and then we check for the attributes that we receive as a consequence of the call. So here you have an option. You can filter out by operations. For example, if you are just interested in files being deleted or files being overwritten, then you can just catch for those ones, or you can just log all the occurrences of that operation happening. And then the last step is get the ACL of the process that is going to operate towards that file. So with this scenario, we can confirm if the process is running with high privilege and accessing a folder or a file that low privilege users have also access to, then this is a potential target, and then we log it in using ETL, which I'm going to cover later. But that's the idea of our DLL, right? That we need to catch this scenario, and if we find a potential target, we log it. So ETW is and the essential idea that we're trying to follow in this way of hunt for these vulnerabilities is like try to make it as smoothless as possible. So we're trying to use everything that is Windows based because most of the engineering workstations run on Windows. So that's what we're trying to do. And ETW is a logging system that is already included on all the Windows systems. And it is used for logging all the events that when your operating system crashes, for example, or any provider within your operating system wants to log something, it is going to be used most of the time through ETW. The cool thing about using ETW is that you don't need to program your own logger, and it is also very efficient. And you can give it some parameters to tell it, oh, you know, I want you to run under a certain circumstance. For example, the size of a file. So it is going to write everything in memory to make it as efficient as possible before writing into disk. So you can specify if the size of the buffer is larger than 1 gigabyte, then write it into disk. So in that way, you can avoid having a lot of writes into your disks, and at the same time, you avoid potential logs. And so that's what we did. We defined that we wanted to write into the file every 7 days to see what was going on. And finally, in order to make this available to every process in the system, we rely on this called appinit DLL. And app init DLL is an infrastructure that allows you to attach that DLL into every process in the system after boot. So you need just to modify 2 parameters in this key. One is the DLL to inject. That app init DLL is a string with a path of the DLL where it is going to inject. And then the load app init DLL is just expects for a 1 or a 0. If you put a 1, that means that it is going to be injected into every process. If it's at 0, it means that it won't be injected. The only caveat with this one is that the machine where you are running this needs to have secure boot disabled. But if you are typically doing hunting, you usually have full control of the system, so you can easily remove that flag. And then the next step is validation. So now this is when these tools come into consideration, because now we have narrowed down the potential targets, and now we can inspect it using these tools, especially the ETW viewer. So that's what we did, and we ran ETW to check our results. And we saw that one of the components that repeated a lot in the engineering workstation that we were trying to do the hunting was this program. And this is typically how you see an ETW log. And we were logging the file, the operation happening, which process was running it, and which file was opening. So we saw this one that was repeating a lot, and this is called pager CFG. And if you remember what a pager was like a small device to send messages. So we saw maybe this program is used to send messages, or we don't know. But we saw that it came from Iconics. So the question here is, what is Iconics?
So Iconic Suite is an HMI SCADA solution. So basically, any ICS facility that is being developed, they can use this suite to automate almost everything that they want to do, right? So they can define devices, connections. They can also set up a lot of alerts. So let's say a pressure in some boiler is rising up, and engineer automatically wants to know what's going on, right? So they can receive some sort of text message or something, and then also they can remotely access that machine to control and open valve, close valve, whatever, right? So all these things can be facilitated using Iconics. They have amazing suite of products, but at the same time, they have over 375,000 unique installations in over like 100 countries. So this is what makes Iconics a really ideal target. They are also spread in a lot of industries, right? Oil and gas, government, military. So a juicy target, I would say. So the interesting part is that it allows the administration to assign multiple roles in the software, right? So there can be admin who sets up everything, and non-admin, some engineer who only controls some portion of the system. And yeah, this is critical, right? We probably want to exploit this scenario and get admin and do things that typically we are not allowed to. So looking into how many devices are using this Iconic Suite, we utilized expense from Palo Alto Networks, and we saw that multiple devices, they are using Iconic Suite's backend server, critical servers, and inside the SCADA systems, right? So we can see this type SCADA. So yeah, yet again, let's refer to the Purdue model. So Purdue model is the model of architecture that is implemented by a lot of ICS industries to define in what level their device should be and how they would communicate with each other. So looking into the Purdue model for Iconics, we found that it operates on level 2 and 3. So on level 2, Iconic Suite can be used to control SCADA devices using HMI, and they can also be implemented on engineering workstation, HMI servers, and writing data into the server, like historian, right? That is also controlled by Iconics, and user access is defined by domain controllers. So it operates on both level 2 and 3, and let's see if we can do something to bypass this. So now we did hunting, validation. Now let's get to the juicy part, exploitation. So now what? How do we exploit that? We know that there is a potential vulnerability, file operation vulnerability that we can exploit, and critical target, right? So how do we go about exploiting that? So one interesting attack avenue is DLL hijacking. We can just plant a DLL, malicious DLL in the folder that Iconics is looking for and inject that into the process. We got several command execution this way, but let's be honest, it's not that interesting as the other vulnerability. So let's move on. We utilized known research from James Forshaw to create and define symbolic links. Just a shout out to his research, really well explained. So we utilize symbolic testing tools to create symbolic links. We'll come to that later. Symbolic link testing tools. This suite only helps us create shortcuts. If you remember from Windows, there are shortcuts. Right-click, create shortcuts. But this is a special kind of shortcut that we are utilizing. So not going into much details about it, but yeah. So how do we use shortcuts, symbolic links, to exploit and affect availability of the system, right? So on the left side of the lower image, we can see that is the UI for pager config. Here, you need to define what kind of device you need to use for sending SMSs. So in Iconics, you can define what happens once some alert is triggered. So an engineer will define that pressure in boiler 1 is rising, and when that happens, SMS will be sent. But how? So that is controlled by this pager config utility. So you can define what device, baud rate, and where to write logs. That's the critical part. So if anything happens, then like how SMS was sent, what SMS was sent, everything is written into the log file. So an admin can define a log file, let's say legit log, and that is configured here. So if we can somehow control where logs get written, then we can control, we can modify or even delete or compromise something critical driver, right? So let's assume that we compromise that log file and exploited that to point to a critical driver, in this case, cng.sys. And if a driver is corrupted, then system won't boot and reboot cycles. So we use this exploit to find the log file path. So what happens is that whenever we modify anything in this UI page, those changes are reflected inside a configuration file. That configuration file is not privileged. So that could be a design issue or whatever, but that is not privileged, and that's the first vulnerability that we exploited. We went through that file, configuration file, and found out that this is the location where administrator is writing logs to. So we found that path, and then we used a symbolic link testing a tool to create a special shortcut. We created that special shortcut, and what happens is that when program starts looking for that log file, it will point to a critical driver. But when any admin opens the configuration utility, they will only see the legit log file. So that way, no one knows why this happened, right? So why did we choose cng.sys? cng.sys is typically a cryptography driver for Windows. It's used for a lot of encryption that is done by Windows on system, but by default, it resides inside Windows, System32, and drivers. Critical part is System32, and inside that, there is a directory, drivers. That's where cng.sys is actually at. But the way Windows is working, not sure why, but if it first looks for cng.sys file inside System32 folder. So what we can do is, we can point log file to cng.sys that resides inside the System32. It currently does not exist, right? So when any alert is triggered and privileged process is trying to write the logs, they have the enough privilege to write inside the System32 folder, and they will create a corrupt driver. So if it gets loaded, then what happens? This is how the typical attack will look like. We can see that any attacker would do something malicious. Let's say a port scan, and there could be a rule that triggers alert for port scanning. It would send the admin that, oh, hey, some attacker is trying to get in. That would trigger an alert, right? Call, SMS, or whatever. But at the same time, the kernel driver, corrupt kernel driver that would get created and crash the system. So let's get into demo.
Yeah, we got it. Okay, so the idea here is the first user doesn't have any admin privilege. There we are checking it manually, but the script we showed earlier can catch where the path of the log file is going to be written, and it doesn't matter because it's going to be accessed. And this is typical for any installer, hard installer, that or anything that creates logs. Most of the time, anyone can access to those logs. So that's dangerous if the process is with high privilege. Now then, we create the link from the log that everyone has access to the critical driver that is going to be corrupted, because remember that that file is going to be written with information from the SMS server, so that's going to be pushed towards that file. Now we log, and since we did not have the SMS server, we just want to do it manually. Now we're logging up with the admin user, and now this one is the user that is going to send the alert, right? And remember, this is now just to see the proof of concept, but actually this alert can be automatically triggered by, for example, an error on a PLC, or an RTU can report something happened in the system, and then this SMS is going to be sent as well. But this is, in order to make it more visible, we are sending a message with the admin account. And now, if we look into the CNG sys driver, we're going to see that now it's corrupted with the information that the log was written with. So there, we're looking for the driver. And if we check the driver, it's now corrupted with garbage, right? Because since we are not able to control the content of the log, we cannot write code that can be executed. But at least now the driver is completely gone. And yeah, it's full with garbage. And then if we restart the machine, it will never come up. And the problem here is, as we saw recently, what happens when a driver is corrupted, right? It's very difficult to fix it in terms of, we don't know at this time which file is the one causing the issues. And many of the users in the industry do not have access to the BIOS and go and repair this by removing the file. And for instance, we don't know which file was the one that is corrupted. So we just get into this endless loop of rebooting the machine endlessly. And why this is important? Well, in the IT world might not seem as important, but on the OT world, we have the priorities the other way around, right? We've take the availability as our highest priority, because we know that the protocols in ICS, most of them are not encrypted, so we don't care too much about confidentiality. So our top priorities are availability and integrity. And here in this case, we are compromising availability of the system. So this was really cool because Mitsubishi had a pound-to-pound project with this with their products, and no one found this issue. So yeah, they released an ICS advisory saying that they are creating a patch to overcome these issues, and we're going to have upcoming publications in this QR code. So yeah, hopefully this or next month we're going to release more details about it. But let's have a summary of what we did and what is going on, right? So first thing is we created a Detours DLL to be able to instrument different functions, in this case, empty create file, because we want to see when files are operating. And then from there, the second step is check the logs once they are done, like in our case, every 7 days. And then we validate it. We use debuggers, CTWs, process monitor to understand from all these results. We already narrowed down different software, and we narrowed down which software is potentially vulnerable. Not only that, but which file is the one that could be exploited. And then from there, we try to confirm if it's vulnerable or not by using these tools. And the next step is actually exploiting it. which is what we did right now. Creating the symlink, we use this exploitation method, but actually that's not the only exploitation method. This is what we did to redirect the content from the log into the driver, so we corrupt it, and then after that, you just have fun or profit. In our case, just fun, because they didn't pay us the bounty. So. And some caveats and limitations is that every time it's harder to exploit these kind of things because Windows protects itself from creating symlinks from non-admin accounts. That's why you need to rely on tools like James for Show Symlink. By the way, that symlink tool is not the same that you have on your computer by default. It's a different type of symlink. That symlink is based on Object Manager, so that's why you can overcome that limitation, but still, every time gets harder. That's how the installation looks of this software, and what Mitsubishi responded to us is that we shouldn't click on Install Genbroker, which doesn't make sense for us because that's one of the options to install the additional tools. However, that's what they were saying, like we shouldn't click on that because it's mostly used just for legacy servers, and they should be used installed as a standalone service. But anyway, I think this still creates an issue, which is low privilege files being accessed by high privilege processes without the proper control, and this is what causes the issue. Thank you.